Hello and welcome to the week three of this discussion session. Myself, Prerak, and I will be taking this discussion session on this NPTEL course and an invitation to topology. So we can wait for a few more minutes if others wants to join, and then we will start discussing problems from assignment three. I hope that's fine. Um, okay, let's wait for a few minutes. So we will start our discussion in a few minutes. Let's wait for a couple minutes more um, for others to join. Okay, now let's start. So I will start with discussing problems from assignment three, and you can stop me whenever you find any difficulty understanding any argument. You can unmute yourself. You can write in chat, whatever suits you. Okay. For those who join later, myself Prerak, and I will be taking this discussion session. This is week three of the discussion session. The first 2 weeks recording are available on my YouTube channel. So let me write down the channel name as well. So if you search on Google my name Prerak, Prerak D Prerak. If you search it on Google, you will find out a channel name, YouTube channel name Maths with Prerak Deep. Okay. In this channel, you will find out the last 2 weeks recording on this course. Okay. And this week's recording will be uploaded on that channel as well. Okay, so that's all. Now let's discuss questions. Okay. So first question is, uh, let x BR, real line, and Y, B, and close one open, close zero open one, union singleton two. This subset of R, consider consider subspace topology on Y defined using the standard topology on R. Then the question is, which of the following following sets are open in Y? Okay. Um, Option A, closed half open one. Option B, 0, comma 3 by 4 open. Option C, close 0, open half. Option D, singleton 2. Okay, so I will give you a few minutes to think about this question, and then we will discuss the solution. Okay. Um, if A to B is a function, if f is a function from A to B, does always B is a proper subset of f of f inverse of B? No, that is not true because function need not to be surjective in this case, right? So there can be images left inside B which need not to be covered. So it can, so B is a proper subset. B can't be a proper subset of this, but this can be a proper subset of B. That is always true. But Kartikeya has already left the chat, so yeah. So Mohana, you try this question, okay, and you guess. Let me know your answers, and then we will discuss the solution. Okay. Do you have any guesses? Um,
So except the first one, all three are
except the
open.
first.
Right? First one.
Right.
Am I right?
Right. Yes, exactly. You are exactly correct. Okay, so let me discuss why is that true. Uh,
Yeah. Please,
so
and also, if possible, sir, if by considering other two topologies,
can
like
you
you have considered R with standard topology, right? I just
right?
wanted to know what will be the difference if we consider R with lower limit topology or K topology? Can you please do this, sir?
Oh, okay. So you just need to know the
And
sub.
one more thing, that Karthikeyan, I think he has messaged in the chat box a question. It was related to one of the one of the assignment question. I think there was a
Yeah,
answer
yeah,
was
I know
wrong.
that. So that question is not true. So whatever option he is written, that is not true. B will always be us. B will not be
Yeah,
the proper subset, but the f of f inverse of B will be the subset of B always.
yeah, but
That's
it was marked wrongly in the assignment, I guess. When you have released the result, answers, there was a mistake, I guess. That is the reason why maybe he has asked.
oh, I don't know. Uh,
Okay, if possible, please look into.
in the current assignment is that wrong? That's what you are saying?
Yeah, it was in the first assignment, I guess. The
And the
first
first
week assignment.
yeah. Was it wrong in the first assignment?
Yeah, whose results were released on last Monday or Tuesday. I don't remember exactly.
Okay.
In that, it was wrongly. The scheme was wrong, is what I guess. That's maybe reason. Maybe he has asked.
Ah, I see. Yeah, maybe
Please.
that under
Yeah,
the assumption that if it's subjective, then it is true. But if
yeah.
it's
Otherwise,
subjective,
need not be right. But it was the. In the answers, it was given that that statement is always true.
okay.
Something like that. Maybe that is the reason he has asked. Sorry.
Okay, that's fine. Oh, that's
Okay.
not on my hand actually. Those are in hand of NPTEL, so it's not in my control.
Okay.
Uh,
To whom? Maybe we have to mention that in the forum, or how we can.
yeah, that's a good point. Actually, I don't know.
Okay.
Yes.
Maybe that's what I guess. Because of that reason, he must have asked, is what I guess. Otherwise, in this class, it is not related, right?
Right.
Yeah,
That's
yeah,
makes sense. Okay.
yeah. Okay.
Good. Yeah. So your question is with yeah, the lower limit topology and the K topology, right? With
Yeah,
the
yeah. Or maybe how that really makes the difference. That can you emphasis on that?
Yeah, so because the open sets will be different in both of the topology, right? So you
Yeah,
will consider in the lower limit topology, you always consider neighborhood which the lower limit is included in the open sets. Okay, these intervals will be called open in that, right? In
yeah.
the lower limit topology.
Lower limit,
So,
right?
yeah, so in that case, if you take intersection, so in that case, this will also be an open set.
Okay,
A
okay.
will also be an open set in that, right?
Okay, okay.
Uh, yeah, but this will not be an open set, right? In that case, B will not be an open set in that.
No, that will be right because it's already open in the standard.
Yes.
Yeah,
Yeah, that will be open in the standard. So, but this will also be included in the limit topology. Similarly, you can also uh, think of in the K topology. You just need to look at that uh, the intersection. How will the intersection will look like with respect to this Y subspace? That's
yeah.
all.
Okay.
Okay, so let me explain the reasoning behind this, and then we can move forward with the other questions. Okay.
Yes, please. Please.
Yeah. Yeah, so when we say the subspace topology, Y has a subspace topology from X, that means an open set in Y is yeah, for an open set in Y, open set V in Y, there is a there is an open set U in the topology of the bigger space, such that V is nothing but y intersection with u. Okay, so if we can find out such open set for any of the options, then we are done. So for example, in case of one, there cannot be any because our original spaces are, and the open sets are nothing but the open intervals, and then their finite intersection, and then their arbitrary union. So uh, there cannot be any open set which will include one whose intersection can be written in this way. Uh, yeah, so there is no open set whose intersection can be like this. But in the case of B, this is itself an open set in the normal Euclidean topology. So this is fine. And if we intersect it with Y, we will get the same thing. And similarly, this is also for, you can take, let's say, -1 comma half intersected with Y, you will get this. And for any smaller subset, for example, 2 minus epsilon and 2 plus epsilon, intersection with Y will get the, yeah. So yeah, this is the first, for the first question. Okay. Okay. Now, question number two. Um, yes. Let x be a non-empty set and Y be a subset of X, be a non-empty, be a non-empty subset as well. Consider the consider the finite complement topology on X denoted by tau FC. Okay, finite complement. That's right. Finite complement FC, and let y be given the subspace topology tau y with respect to tau FC, and let tau FC y denote the finite complement topology on Y, then which of the following are true? Okay. Option A, the finite complement topology with respect to Y on Y is strictly finer than the subspace topology given on Y. The finite complement topology is strictly coarser. The subspace topology These topologies are incomparable. The Yeah, option C is both of the topology are same subspace topology and the finite complement topology with respect to Y, and both are the subspace topology and the finite complement topology in Y are incomparable. Okay. So again, I will give a few minutes to discuss, to think about this question, and then we will discuss the solution of this question.
Sir, I'm actually lost with the notations. It would be fine if you just explain. And no one, I mean, no one else is there in the meeting as well.
Yeah, okay, okay. Uh, yeah. So you want me to define notation?
No, no, I mean, notation, I mean, that, and explain this answer
Okay,
also.
okay, yeah, sure, sure. I will do that.
Please.
Yeah,
Yeah,
yeah, I
please.
will have to do that. Yeah. So before that, you asked me one question about the K topology on this, right? So let me discuss that. I discussed the lower limit topology with you. So
Yeah, yeah, you said A is also an answer, right?
yeah, but what about the K topology? So in K topology, you remove the basis of the K topology are what? So those are precisely intervals A comma B, and you remove this K set, right? Where K is what? K is the 1 over n going to n is a natural number. So you remove this set. So it will only affect this if K is a subset of the interval. Then only this will make sense. This is removing K from the set will make sense. Otherwise, it will not make sense. So in other words, if zero contains inside the set, and if take any open interval containing zero, then only removing K will make sense. Okay. So now you need to think of you have to think of which of the following set can be open in R9, right? Yeah. Now, which of the following set can be open in that K topology standard in the K topology on R, right? So, for example, if I take this first set, so now this first set, uh, half is uh, you can take Right. So will half this subset will be part of that? Mm.
Yeah, that's what. Only one is the option that you need to think. Others three are naturally open, right?
D option is clear. That is open. Um,
No, because K topology is finer than the standard topology.
yeah, that's true.
Whichever is already open in the standard will be naturally open in the K topology also, right? Am I right or no? I don't.
Yeah, that is fine. So in the first case, I'm thinking because half will be excluded from the interval, um,
Yeah.
and then if you think of it as a intersection with y, uh, okay, let me think. Hmm. Okay, so yeah, what we can do, we can. I will come back to this question because the statement that you are saying that because it's finer than that. So finer means that the open set, uh, yeah, open set should be part of that because it can be written as the union of the other set that is there. Hmm. So it should be part of that. Okay, yeah, you are correct in that way. But we are working with the basis elements here only. So in the basis, in terms of the basis, we only look um, if there is a given a base, if there is a bigger basis, then you just find out the smaller basis from the other topology to show that whether it is finer or not. So it is finer in that sense, and you can always do that with the standard topology and the R lower limit and the RK topology. Hmm. Okay, so I will come back to this. Let me first discuss this question number two. Then. Okay. Yeah. So what do we have here? We have a subspace topology on X, right? And now we are considering the cofinite topology. Cofinite, yeah, finite complement topology on X, and we are denoting it by tau fc, which is represents the finite complement. And y we given the subspace topology tau y with respect to this. Okay, so y has one topology. So first of all, X has tau fc, and then y is given the subspace topology from this. Yeah, which we call to be tau y. Okay, this is coming from X. And then y also has another topology we can define, which is the finite complement topology on y, which is uh, irrespective of the topology on the bigger space. Now we want to compare these two topology. That is what the question is. Okay, which one is finite, which one is coarser? So yeah. So now let me first write down the open set. How does these topology look like? So in case of tau X, sorry, in case of tau FC, which is a topology on X. So this is on X. Tau FC looks like set of all open sets, subsets of X, such that the complement X minus U is finite set. Okay. It is a finite set. Um, and then on Y, we define this topology, which is the subspace topology from tau FC. So we say that the open set will look like V in Y, such that V is of the form of U intersection X. U intersection Y, where U is in tau FC. Okay. Now tau YFC is what? It is the subsets of U, subsets of Y, such that the complement of U in Y is finite set. Okay. So we have these three definitions. Now we need to compare these sets. Right. That is what the question is. So now let us first compare tau Y with tau, the finite complement topology on Y and the subspace topology. So first let us see this. So for that we start with an open set W in tau Y. Okay. Now because it's a subspace topology, so there has to be some open set in X, in tau FC, such that this can be written as this for U in tau FC. Right. Okay. And now once you have this U intersection Y, now what does this say? Now what is U? U is nothing but X minus a finite set A1 up to AN. Okay. This is U is by definition. So if you consider the intersection, this intersection, so it will be what? It will be intersection of these things, right? So if any of AIs belongs to Y, okay, so that will be removed from Y. So this will be equivalent to say that this thing, right? This thing is equivalent to say that if where BJs are those AI that belongs to Y. Okay. And if there is none such, then you will get the whole Y as the intersection. Okay. Mm, yeah. Right. So this will be the set. And what is this now? Now this is a finite. Now this is nothing but a element in the finite complement topology. So this is some V which is belongs to finite complement topology on Y. Okay. So this implies that given a U in the subspace topology, given a W in subspace topology, that also belongs to the finite complement topology on Y. Okay. So this proves the one side. So this implies uh, that tau Y is contained inside tau YFC. Okay. Is this clear? Is this part clear?
Yes, sir.
Good. Now let's look at the other part. So tau yfc, you want to show that it is contained inside tau y, the subspace topology. Okay. So for that, we start with w in the finite complement topology in y. So what does this mean? This means that w is nothing but v intersection y. Sorry. This means that w is nothing but y minus some finitely many points b1 up to bk, right? So now, can you think of any subset u of x such that u intersection y can be w? Okay. And the answer is yes, one can just, instead of y, you just think x. If you remove these finite element set from x, you will get q. So if you consider your u to be x minus this finite element set b1 up to bk, okay, and if you intersect it with y, you will get w. Okay. um, so this implies what? This implies that uh, yeah, and further notice that u is an element in tau fc. Okay, it's in the finite complement topology of x. So this implies that um, that w is in the subspace topology of y, and in the end we can say that we started with the element in the finite complement topology and we get that element to be part of the subspace topology. So that means this is true. Okay. Now when these two things are true, we will get tau y fc is equal to tau y. Okay, this is equation b, this is equation a. Now from a and b, we get this. This is this argument fine?
Yes, sir.
Good. Okay. Now let us look at another question. Yeah, so this means that option C is true in this case, that both are equal. So this is actually very nice uh, result, because it doesn't matter if you start with the finite complement topology on x or on y, you get the same in the subspace topology. You get the same thing. So that is actually a nice observation. Now let x tau be x tau be a topological space, and y1, y2, y3 be subsets of x, be subspaces. These are not subset, these are subspaces. That means that y1, y2, y3 has subspace topology on it. Now for two topological spaces x and y, we use the notation y triangle x if Y is a subset. That's the first condition. Second condition is that the topology on Y, okay, is the same as the subspace topology on X. So topology on Y is same as the subspace topology on Y from X. Okay. Now the question is, which of the following is true? If Y1 triangle Y2 and Y2 triangle Y3, then Y1 triangle Y3. Option B, if Y1 a subset of Y2, Y1 triangle Y3 and Y2 triangle Y3, then Y1 triangle Y2. And if Y2 a subset of Y3, then Y2 triangle Y3. Okay, so again, I will give you a few minutes to think about this question and then we will discuss the solution. Okay, now let me discuss the solution to this problem. Uh, so we have the topological space x tau and y1, y2, y3 the subspaces. That means they have the subspace topology on them. Now for two topological spaces x and y, we use the notation x triangle y triangle x if y is a subset of it is a subset of x, and the topology on y is equal to the subspace topology on x on y from x. Okay. Right. So we use few notations. Uh, so denote tau yi for the denote this the subspace topology induced from x. Okay, for each I1 to 3. Okay, and denote tau yj uh, the subspace topology on yi sorry on yj induced from yi if yi if yj triangles with yi, right? Then only we can have the subspace topology induced from yi. Okay, on yj. Okay, so with this notation, now let us start with question number problem the statement number 8. So statement A says if y1 triangle y2 and y2 triangle y3, then y1 triangle y3. So yes. So what does this mean? So we have from this we know that y1 has topology induced from y2. Okay, the subspace topology. From this we know that y2 has topology induced from y3, right? And y3 has topology induced from x. So the question is, so the question can be broken into these two parts. In order to prove this, you need to first show that y1 is a subset of y3, and the second part is that the subspace topology on y1. Okay, the topology on y1, which is in this case the subspace topology induced from y2, is equal to the subspace topology induced from y3. So this thing you need to show. Okay, is the question clear now?
Yes, sir.
Okay, good. So um yeah, so now why first is true? Because we know that y is a subset of y2 because of this relation, and y2 is a subset of y3 because of this relation. So it will show that y1 is a subset of y3. That is clear. So this is already true because since y1 is a subset of y2 and y2 is a subset of y3. Okay. Now let us look at the second part. So again, for the second part, we will prove the containment from both sides. Okay. So first we will try to prove the one side containment, that this is contained inside this. Okay. So again, for that we start with a open set in the first topology, Okay. Um, so what does this mean? This means that W has to be equal to some U intersection with Y1, where U is in tau Y2. Correct? Yeah. And now topology on tau Y2, sorry, on topology on Y2 is coming from Y3 because of this earlier assumption that Y2 is having the topology from um, Y3. So we use this topology over here. And now which will further imply that for U, there, there will be some V whose intersection with Y2, and this V will be in tau Y3, right? And now this tau Y3, hmm, now this tau Y3 is what? Tau Y3 is, yeah, tau Y3 is nothing but there will be some U naught intersection with Y3, correct? Um, okay. Now we want to show that W is in this. So W has to be of the form that some U intersection with Y1 where U is in tau Y3. And which will be just nothing but U naught intersection with Y1, correct? And here also you will get this is nothing but U naught intersection with Y1, where U naught is in uh, because look at this. This is Y1 is the smallest subset in this. In the end, you will get U naught intersection with Y1. So that is what we are getting over here. So this intersection is okay. So I can write it in this way that U naught intersection Y3 intersection, now intersection with Y2 and intersection Y1 will give you Y1 only. Now this intersection will give you Y1. Okay, so you get Y1 only. So you get this thing. So now what does this imply? This implies that um, so this implies that, and this U naught is in Tx. Sorry, yeah, Tx. Now what does this imply? This implies that yeah. Now this is the open set in Y3. Okay. Um, which we had earlier called it to be B intersection Y1. So this implies that this is, and this is W. So this implies that this is an element in T Y1 with the topology in Y3. Okay. because V is in uh, Y3, right? Okay. So this implies that W is in T1 Y3, uh, which implies that T1 Y2 is contained inside tau Y3 Y1. Okay. I hope this argument makes sense to you. Um, okay. So for those, yeah. So Anjali joined just recently. So let me explain what we are doing right now. So we are discussing this problem uh, where X tau is a topological space, Y1, Y2, Y3 are the subspaces of X, and the given two topological spaces X and Y. We use this notation if the topology on Y is equal to the subspace topology on Y induced from X, and Y is a proper subset. Y is a subset of X. Then we need to show that which of the following is true. So we are first right now we are discussing the statement A, and in the statement A we need to show uh, that Y1 is subset of Y3, which is clear from the other two uh, relation. The topology relation we are proving right now that both topology induced on Y1 from Y2 and topology induced from Y3 from Y1, they are equal. Okay. So this is what we are proving right now. So we have proved one side of it, that tau Y2 Y1 is contained inside tau Y3 Y1. Okay. And the notations are pretty self-explanatory because uh, tau Y2 Y1 says that topology on Y1 induced from subspace topology on Y1 induced from topology on Y2. That is what it says. Okay. Okay. So now let us discuss the other part of the question. So, okay. So again, we start with an open set W in this topology, which is induced from Y3 on Y1. Right. Now, what does this mean? This means that W has to be some open set intersection with Y1, where this open set V comes from the topology, subspace topology from Y3. Right. Okay. So we have this thing to be given. Now, what is um, now this is what V is, what V is nothing but X intersection U3 intersection U1. Right. So this will um, sorry, what I'm saying is, so V is nothing but, now V, now since V is an element in Y3, this implies that V is nothing but, V is nothing but, sorry, V is nothing but U naught intersection with Y3 for U naught in tau Y, yeah, tau Y3. Uh, yeah, tau X, where X is the topology on X, right? Okay, so W can be written as U naught intersection with Y3 intersection with Y1, which is nothing but U naught intersection with Y1. Yeah, so this is nothing but uh, a subspace topology on y1, right? And if you want to prove that it is an element in tau is an element in y1 y2, that means you need to write it down it as some u intersection with y1, where u is in tau y2, which is induced from y3, and then you can further break it down it as um v intersection with y2 intersection with y1, okay, and so on and so forth. So okay, so give me a minute. There seems to be a problem, not problem, but yeah, there is a problem. The statement that I started with, that has a problem. Hmm. Okay. Yeah. So this relation says that topology on Y is equal to the topology induced from on Y. So then we have this relation. So now topology on Y that we need to consider is not coming from this thing. It should be topology from the subspace topology that is already has. Okay, that means tau one. And yeah, so we need to compare not these two topology, but we need to compare the topology already it has, which is tau y1 and tau topology induced from y3. Okay, now it makes sense, right? Okay, so I hope the clarification is clear to all of you that I just made. We need to compare the topology already y1 has with the topology that it induced from the y3. Now, what topology does y1 already has? Y1 has the subspace topology. Okay, so subspace topology from X. That's what we will call to be tau y1. And it induces a topology from y3, which we will call it to be this. And now we are comparing these two topology. Okay. I hope this clarification is clear to all of you. I made a mistake over there. Uh, I got confused with the topology that we need to compare. But now I think it is clear to me. I hope it's clear to you as well. So now the question is to now subset argument is still the same, but we need to now compare these two topologies. The subspace topology on y1 is equal to this the subspace topology on y1 induced from y3. Okay, right. So first we will show the one side containment. Um, so yeah, so the argument will remain as it is. So we start with open set W in this subspace topology. That means it is nothing but yeah. So that means it is nothing but um U intersection Y, where U is a subset, where U is open set in topology X. Okay. And now since y1 is yeah, now since y1 uh, triangle relation with y2, that means the tau y1 is same as tau y1 induced from y2, right? That is what it means. So yeah, that is what it means. um, okay, so now here is a clever argument. Because y3 is, because y1 is contained inside y3, we can rewrite w as u intersection. Since y1 is contained inside y3, this implies that the intersection of y1 and y3 will give you y1 again. So we can rewrite y1 as y1 intersection y3. So w is nothing but this. This is nothing but this. Okay, and then the set intersections are associative in nature. So you can consider this intersection and this. Now u intersection y3 give you will give you a open set in uh, tau y3. Okay, so now v is u intersection y3, that is v is in tau y3. Okay, so this you will get. Now what does this mean? This means that now w can be rewritten as an element in the subspace topology induced from y3 on y1. Okay, hence this relation holds, the containment holds. I hope this argument is clear. This is the neat and clear argument.
Yes, sir.
Okay, now the other argument is much simpler. uh, so right, so again we start with an open set in this topology, and then what does this mean? This says that w can be rewritten as the intersection of an open set in tau y3 with y. Okay, so let's call that open set in tau y3 to be u and intersected with y. So this u is in the topology tau y3. Okay, so now once you have this, um, you can again, now you expand the expression for u. So now since u is in tau y3, there is open set v in tau x such that u is nothing but x intersection with y3. So using this argument fact, we can rewrite w as sorry, v intersection y3, v intersection y3 intersection y1. Okay, Now, as I said earlier, the intersection property, intersection of sets are associative in nature. You can now consider this intersection. Now, since y3 contains y1, this implies that the intersection of y1 and y3 must be equal to y1. So this will give you that w is equal to v intersection y1, which which implies that w is an element in tau y1. Okay, so we started with element in tau y1, tau y3 y1, and we get w is the element in tau y1. So this implies that the topology induced on y1 from y3 is contained inside the topology induced from x on y1. Okay, so this completes the proof of the fact that tau y1 is equal to tau y1 y3. Okay, so this and this together with the so this gives you that y1 also triangles with y3. So that means the statement A is true. So the following are true. Okay. Now similarly for y1 for y2 as well. Okay. So for y2 as well, we need to show that thing will happen. So for y2 also, for B also, this thing will hold. Okay, I will give a quick argument to that. So y1 is a subset of y2. Y1 is triangle with y3. Y2 is triangle with y3. And then you need to show that y1 also triangles with y2. So statement B says y1 is subsets of y2, and y1 triangles y3, y2 triangles y3, then y1 triangles with y2. Okay, so since y1 is already a subset of y2, we only need to show that tau y1 is equal to tau y1 induced from y2, right? So we start with this first side containment. So let's say w is in tau y1. That means w can be rewritten as u intersection with y1 for u in the topology. Um, yeah, in the topology from x of x. Correct. Now again by the similar logic, since y contained in y2, we will get y1 intersection y2 to be y1. So you can rewrite y1 as the intersection. So you will get u intersection with y1 intersection y2, and this can be further rearranged using the associativity of the intersection to this. And now u intersection y2. Now u intersection y2, uh, u intersection y2, let's call that to be v, is an element in tau y2. Okay, so this will imply that w is nothing but v intersection y1. Okay, so this will imply that w is in the element. Yeah, this implies that w is in this topology that it's induced from is in the subspace topology induced from y2. Okay, so this implies that the one side containment. Okay, similarly for the other side containment, one can also give the similar argument. Let's not discuss that. um yeah, so similarly we can show that tau y1 y2 contain inside tau y1. Okay, I skip the argument for this. That's an exercise for you guys to do. So this statement B is also true. Now statement C. Now statement C was, if y1 is a subset of y3, then y2 triangles with y3. Okay, so y2 is a subset of y3, then y2 triangles with y3. So we only need to show that tau y1 is equal to tau y2 y3. So again, the argument that I just gave for this argument will be directly applied to prove this fact. Okay, so this argument can be directly used here to prove this equality, and then you will be done. So this completes the all three statements. So both all three statements are true. Okay. Uh, yeah, and this completes the proof. Okay, now let me ask you any questions. Any questions on any of the proof? Okay, good. If there are no questions, then we can move ahead and discussing more problems. Hmm. Okay. Now questions. Now I will discuss a question from the product topology. Let X be this interval and Y be the whole space R with X having the subspace topology and Y be the standard topology on R. And which of the following subsets are open in the product topology on X times Y? Option A is, option B is, option C is, option D is. Okay, so I will pause for a minute, and then we will discuss the solution. Till then, you can think of the solution and let me know. Okay. So Rudra has said A and D as the options. Okay. So now let us see. So X is a closed interval 0, 0.1. Y is R. X has a subspace topology. So you need to consider the open sets will be the intersection of open sets from Y with X. Okay. And in the product topology, what are the open sets? In the product topology, open sets are the so we talk about the basis of open set. So what are the basis of product topology? Sorry. Uh, those are nothing but the product of open sets from each of these either of the space. Okay. Product of open sets from both of the space. So basis of product topology are U cross V, where U is in tau X and V is in tau Y. Right. This is the product. This is the basis of product topology. And once you have the basis, the topology generated by them is nothing but the infinite arbitrary union and finite intersections. Okay, that's what the topology is. Okay, and keeping that in mind, now let's come back to the problem. So, because these are just given to be the product in product, it's not given in the union or intersection. We just need to say that whether each of the component, each of the product uh, component is open or not, okay, in their respective topologies. So now let us first look at the first option. In the first option, the closed, sorry, open 0, closed 1, this is open in tau, yeah, this is open in tau X, right? Because it can be written as this intersection with X, so it is open in tau X, right? Similarly, uh, open this, but this is not open in tau Y. Why? Because Y, which is R, has the standard topology on it, and in the standard topology, this can't be expressed. Okay, this open 0, close 1. So this is not an open set. This is not open set in the product topology. Now, what about B? What about B? So B, again, this open close 0, open half can be think of as the -1 to half intersection with X. So it is an open set in X, but in singleton 0, singleton 2 is not an open set in uh, standard topology on R. So again, this is not open. This is not open. Option C. In option C, you have given this, which is again can we think of as intersection with intersection of interval with X. Okay, but and the other set, which is -1 to 1, is also an open set in Y, which is open set in the standard topology on R. So this is correct. Option D with a similar reason is also correct. Okay, so option C and D are correct options. Yeah. So Rudra, you said A and D, so A is not correct. C and D are the correct options. Okay. Are these options clear? Are these answers clear to you?
Yes, sir.
Okay, good. What about others? Are they here or options are clear? Okay. Anyways, um, good. Anyways, let's move on to discuss few more problems. Okay. Now discuss a problem on box topology. Okay. Question number question number 7. For each natural number n, let xn be R. Okay. With standard topology. We consider the infinite Cartesian product R omega to be the product of xn with the box topology. Now, which of the following which of the following sets are open? This is our question. So option A, uh, product of infinite product of open sets un, where un is nothing but open well. Option B, infinite product of open sets with un nothing but minus 1 over n to 1 over n for all n natural numbers. Option C is infinite product of un with un to be singleton 0 for all n. And option D is um, arbitrary product of un with un to be 0 for all for n equal to 1 to k, and after k from k plus 1. Okay, so for u k plus 1 it is r. So for j greater than equal to k plus 1 it is r. Okay, again I will give you a few minutes to think about this problem, and then we will discuss the solution. Okay, so in the box topology, the basis elements are the product of open sets. Okay, uh, yeah, product of open sets will be the basis. Yes, open sets in for each xn. Okay, so the product, this is nothing but a product of infinite long product. Okay, and now each component in that product has to be open in their respective topology. And in this case, what is that respective topology? It is nothing but uh, R with standard topology. Okay, so yeah, so it has to be open in each of for each n in R. That is what simply it means. So B, D, and AB, these are quite opposite answers to each other. Okay, let's discuss that. So as I said earlier, the open sets in the in this box topology only D. Okay, is a product of open UN for each. So okay, let me write it this way. Is where for each n UN is in the topology of Xn. Okay, so this is the open set in box topology. In our case, for each n in the natural numbers, Xn is R. Okay, Xn is R. So UN, uh, so for each n in n, Xn is R. So UN uh, is nothing but open set in the standard topology of Rn. Open set in R with the standard topology. Okay. Um, okay. So now in this case, um, let's look at the option A. So in option A, each n is an open interval. Okay. An open interval is an open set in R with standard topology. So this is true. Okay. Because each un is an open set in Xn. So it is true. Similarly, option B is also true because for each n, un is an open interval in R. Okay, so it is also true. Option C is false because un are singletons, singleton 0. And singleton 0 is not an open set in R, it is a closed set in R. Okay, so un equal to 0 and their product, infinite product, will not be an open set. So all of them needs to be an open set. It shouldn't be like some of them are open set and some of them are not open sets. All of them has to be an open set. Okay. So this is not true. Similarly, in case of D, finitely many sets are singletons and rest of them are R. R is an open set in R, but these for finitely many sets, 0, is uh, singleton 0 is not an open set. So this will contradict the definition of open set. Each of the ends be open in their respective topology. So this will also not true. So option A and B are true. And I think Anjali said the correct answer, right? Yeah. Okay. So I hope the explanation is clear to all of you.
Yes, sir.
Good. Okay. I have a similar question and then we will stop after this. I have one more question of the similar type, but it's on the product topology. Uh, like the infinite product, but with this product topology. So for each n in R, n in the natural number, let x to be the R with the standard topology. Now we consider the infinite Cartesian product R omega. So this is a similar set that we defined earlier in the previous case as well. So the set is similar, but the topology in this case it is different. But with the product topology. So now, what is the difference with the product topology and the box topology? In box topology, you have noticed that the open set has to be the product of open set, where each of un is an open set in Xn. But in case of the box, this is box topology. But in case of the product topology, it has to be product of open sets, but only finitely of them. Finitely of them are can be any open set for x, for I smaller than this, and for I uh, larger than k, it has to be whole of the space Xn. Okay, and this indexing set can be any arbitrary. It can be anywhere in these things. Okay, it need not to be the first k needs to be that. It can be anywhere. Okay, but only finitely many, uh, except finitely many options, all of the other open sets has to be the whole space Xn. That is the difference between the product topology. So this is called product topology. Okay, right. So clearly you can see that the box topology is much finer than the product topology. Okay, so product topology is coarser than the box topology. That the first observation you can clearly you can make just looking at this thing. Okay, now with this, let me give you the options. Okay, so option A is a product of un with un to be minus 1 over minus 1 over n to 1 over n. Okay, option B will be product of un with minus with this interval, but for only for finitely many n's, and rest of them are r. Okay, the third is the product of un, where un is nothing but the pre-image of sine inverse of minus n to n. Okay, and option D is product of un with un to be the singleton 0. Okay, again I will pause for a few minutes and then we will discuss the solution. Okay, option B. Okay, somehow my tab, this, I have already written down all these things, but it is appearing slowly on the presentation. So just wait for a minute. I have written down all the solution. Yeah, now the question is there. So I will wait for a few minutes and then we will discuss the solution. Option B is correct. Uh, what else can be the answer? Option D is correct.
Sir, option C is the same as option B.
Yeah, that is true. No, option B and C are not same. Option B and C are not same, but hello. Yes. So okay. So the answers, correct answers are option B is correct and option C is also correct. Uh, Option A and D are not correct. Option A is not correct because each of UN is an open interval. Okay, but in the product topology, we want only finitely many, except finitely many uh, open sets. All other open sets has to be the whole space. Okay, so that's why this is not correct. Will be an open set in the box topology, but it is not open in the product topology. And this is also a counter example why this is coarser than the box topology. Okay. Now, second option is correct because only finitely many UNs are intervals and rest of them are the whole space R. So this exactly fits the definition. Okay. Now coming back to C. C says that it's a pre-image of an open interval minus one minus n to n. Now the image of sine function, the codomain of sine function is just minus one to one. It's an interval. Domain of Okay, so yeah, that is true. Not open minus one to one, it's closed minus one to one because sine attains one and minus one at pi by two and minus pi by two. Okay, so sine function is a function from R to this interval. It is a well defined function from this to this, right? From R to minus one to one, and sine inverse of minus n to n will sine inverse of minus n to n, this pre-image will give you the whole R, okay? Because it contains the codomain, it contains the range of the function. So it will give you the whole R. And since so each of UN is nothing but R. So this is nothing but R. Each of UN is nothing but R. So it is nothing but the product of R. So because of that reason, it is an open set in the product topology. Okay. Now D option is wrong because UNs are not open in the topology. UNs are closed. So that's why D is also not correct. So option B and C are correct. Okay. I hope this makes sense to all of you and it's also clear to you.
Yes, sir.
Good. Yeah. Welcome everyone. Thank you for joining, and I will hope to see you next week as well. Uh, okay.
Thank you, sir.
Yeah. Welcome. No problem.
Sir, sorry for joining so late, sir. I
That's
had
fine. That is fine.
yes, sir. Sir, jam exam just got over.
Oh, okay. Okay. Good.
Yes, thank you, sir.
Yeah. Bye.